All right. So a couple of quick housekeeping things on the Moodle page. Okay, there are two new links now. One to YouTube playlist of class recordings, and another to Google Drive class notes. Okay, the annotations that I make in the class, the um, markups that I make on the class notes, they're all going to be available on Google Drive. And here is the link for you. Okay, and also the YouTube recording of this class and all our classes, Engineering 17, are going to be available on YouTube. And the playlist for that is on Moodle as well. So that's one thing. And another thing I want to remind you, this is something I talked about yesterday as well. The other thing is for you to sign up for notifications. Okay, what you want to do is when you log on to your Canvas, so I'm on my Canvas now, and click on the top left of the page where there's a little profile picture of yours if you so chose, but it's located right underneath the Sac State emblem. Okay, right there. When you click on your profile page, it pulls out a um, dropout menu. Now under that, you want to select notifications and make sure, if you did not already, to select this announcements. Okay, this announcements activity, that should be selected as a green check mark. Okay, that's so you receive important announcements immediately. I need to have confidence in the fact that when I post an announcement, that is made available to everybody. Everybody signs up to receive the announcement. Okay, that's quickly what you want to do if you did not do so already. All right, last class, let's quickly review just a little bit of what we did in the last class. I know I'm not a big fan of what we did in the last class, a whole lot of theory, very little problems. So that's not what I really like. Okay, I really like to do more problems in the class. That is what um, adds more value to the videos that are already posted by Tetro. Okay, so I'll do more problems, but please bear with me as we have to go through a little bit of theory before we get to the problems. Okay, that's what we did yesterday. Yuck, yikes, I don't like it, but it's a necessary evil. Okay, hopefully from today's class, we'll be able to do more problems and less theory. And for the following classes, more and more problems and little lower and lower amount of theory. Okay, so this is what we did in the last class. I showed you a typical engineering design process. Okay, you start with specifications, you design a model, you test your model over and over again, and when you're confident that your model meets this specification, you design a prototype. Then you test the prototype, and when your customer is happy with the initial prototype, that is when you actually commit to large scale fabrication of the device. Okay, so that's the typical engineering design flow. There is a lot of successive refinement that is informed by testing. Okay, testing is very important. That's what we did in the last class. And as engineers, we like to find technical solutions, okay, using some kind of optimization problem. We like to find technical solutions to societal problems, small and large. Okay, this is a profession for us. We make a living out of this. So we are operating at a much higher stage compared to hobbyists. Okay, then we looked at the units. Because numbers are important to engineers, units are important. We need to have a standard way of measuring things. Okay, that's where SI units comes in. And then I gave you the fundamental quantities, and this is a review of what you did in the previous courses: fundamental units and fundamental quantities. Okay, and from the fundamental quantities, their definitions, we have derived units and derived quantities. Okay, so frequency, force, energy, power, electrical charge, potential, resistance, conductance, capacitance, flux, and inductance. Those are the derived units that I have listed here. There are more, but I'm not listing them all, okay? But I have listed the important derived units that are relevant to us, okay? And then we should be fluent in converting from any unit to standard units, number of meters per mile. For example, we do one example, and then we did another example corresponding to the battery and charge time. Okay, here are units of, um, here are powers of 10. Okay, powers of 10 because engineers have to deal with extremely large numbers and extremely small numbers and everything in between. We have to have a shorthand, a handy way of representing extremely large numbers and extremely small numbers and everything in between. Okay. Then we define voltage and current. Both voltage and current are artifacts of charge. When charge separation happens, it leads to what is known as potential difference or voltage. So charge separated is voltage, charge moving is current. Okay, movement of charge is current, motion of charge is current, separation of static charges is voltage. Okay, so voltage is dW over dQ. Okay, and then current is dQ over dt. Okay, you can express, you can call it as time rate of flow of current. Okay, and then we looked at the basic circuit elements. Basic circuit elements, and typically how RLC circuits, the two terminals coming out of the RLC circuits, one is for one for input and output each. Okay, and then we talked about a very important concept, a very important concept. First of all the techniques that I mentioned, you're going to pick up in this class. Okay, the first technique is that of passive sign convention. Okay, the idea is, and let me stress that again, the direction of current. Okay, let me show that using the arrow here, the arrow head pointing from left to right, that shows the direction of current. That is from the positive to negative voltage. Then the current is positive. Okay, on the other hand, if the direction of current is opposite, or in other words, from negative to positive voltage, okay, if the current is oriented in the opposite direction from the negative to positive, or the voltage gain, then I call it a negative current. Okay, so this is a convention. This is typically what I like to apply over and over and be consistent with it in my problems, just so I do not mix things up. Okay, so the idea is that I consider a current positive when it is aligned along the voltage drop, and if it is against the voltage drop, then it's a negative current, negative I. Okay, this is negative. That's the positive sign convention. And when we do power times I, let me talk about it on the next slide. Okay, power is V times I, right? So that's the positive sign convention. Okay, passive sign convention. Then we talk about power, which we derived to be V times I. Okay, we derive power to be voltage times the current. Okay, and then it's a power could be delivered or it could be absorbed. Okay, an element could be delivering power or absorbing power. Okay, for example, a car battery, okay, is delivering power when we turn the ignition on, when we leave the headlights on with the engine off. Okay, so or the radio. So the battery is supplying power to all of these devices. Okay, or it could be charging, it could be absorbing power when the engine is running. Okay, so the same element sometimes could be delivering and absorbing power. And how do we determine if an element is absorbing or delivering power? Okay, that depends on the sign of the power. If the product V times I is positive, then we say the element is absorbing power. Okay, if it is negative, V times I, or in other words, when the current is opposite to the voltage drop, then we say it is delivering power. And like I mentioned, sometimes the same circuit element could be absorbing at times and it could be delivering at times. Okay, this is what we did in the last class, more reiteration of passive sign convention. In this case, okay, in the last example, let me do this one more time. The current, okay, the current is aligned, okay, from the positive to negative terminal. Therefore, the current is positive. Therefore, V times I is positive, meaning that the power is absorbed. In this case, in C, it is delivered because the VI product is negative. Okay, VI product is negative, it is delivered. Similarly, VI is positive in case of A, therefore it is absorbed. And the opposite is true here. VI is negative, therefore the power is delivered. Okay, so that's the thing that we want to remember. This is what we did in the last class, a passive sign convention. And then we looked at a small problem where we look at charging an iPhone 5 battery. We looked at two problems actually. Okay, the last problem told me that P equals to energy over time. Okay, that's the idea I'm using here. VI, so this guy, 5 times 0.5. 0.5 is I, 5 is volts. Similarly, 5 is voltage, 0.1 is current. So when I'm charging my iPhone battery using the same voltage of 5 volts, but different currents, okay? Different currents. And we are trying to calculate the time it takes to charge the battery. When I'm using a larger current of 0.5 amperes, it takes me about 2.5 hours, as opposed to charging it using 0.1 volt, 0.1 amperes, which takes me a lot longer time. Okay, small current charges slowly, large current charges quickly. Okay, so that's the idea. So this is what we did in the last class. Okay, questions, please. Questions so far. Okay, so let's move on to chapter number 2. Okay, very interesting. It's interesting because we begin working on problems here, interesting problems. Okay, before we work on problems, let's quickly review some basic concepts that you're already familiar with from your previous class, and then we'll move on to talking about interesting problems. So far, the techniques that we saw was passive sign convention. Okay, we looked at passive sign convention so far, and we'll keep adding to this list. Okay, we'll keep adding to this list of um, techniques that we will develop through this course. Okay, so let's look at voltage sources. Typically, I'm going to look at two different kinds of sources. One kind of device that produces a constant voltage across its terminals. Okay, independent of what is connected across it. Does not matter what you connect across it. Within certain physical limits, the voltage across this guy is constant. Therefore, we call it a voltage source because it provides a constant voltage. On the other hand, there can be another kind of device that provides a constant current. Okay, independent of what is connected, independent of what is connected across the um, terminals, the current is constant. Okay, therefore we call it a constant current source. Okay, constant current source. Okay, this device on the right produces a constant current and it sets up a constant current. Okay, across what is across its connections, across its terminals, through its terminals. Therefore, it's called a constant current source. Then we will come back to talk about dependent sources. So both of these are independent sources. But we'll come back to talking about dependent sources. Okay. So first of all, what is a source? Okay. A source is a device that is capable of converting a non-electrical energy into electrical energy. Okay, that's the idea of a source. Okay, so sometimes the other way around is also possible. For example, a lead battery, okay, converts chemical energy into electrical energy. As you know, it's a fundamental law of physics that energy cannot be created or it cannot be destroyed. Okay, so it can only be converted from one form to another form. Okay, a dynamo is a machine that converts a mechanical energy into electrical energy. Okay, so motors and generators, you'll look at this when you take your power systems courses. Okay, there are more examples, but when I say a source, it is simply converting some kind of non-electrical energy into an electrical energy, and that's what I care about, the electrical energy. Okay, so here is a voltage source. Okay, the voltage is constant. You know this already because I mentioned it in the very beginning, right? For a voltage source, the voltage is constant. Okay, so or in other words, the voltage is set independent of what is connected across it. Does not matter what you connect across it. Okay, the current is really set up by something else. Okay, what is connected external to this voltage source, that determines the current. Okay, it is not, it doesn't have to be constant, it is set by the load. Okay, but what is important is the voltage across the terminals of the voltage source, and therefore the voltage across the two terminals here is set to be a constant voltage Vs. Okay, the current again, the amount of current flowing through that is set by the external circuit load. Okay, but that cannot change. The amount of current does not change Vs. Ideal voltage source. Of course, this is ideal. There's no such thing as ideal voltage source. There are physical limitations to this behavior. Okay, but the idea is that the voltage is constant across the voltage source. Similarly, for a current source, the current is set. For an independent ideal current source, okay? For an independent ideal current source, the current is set across its terminals. It doesn't matter what I connect across its terminals, okay? Even if I connect a large resistance, a small resistance, does not matter, okay? The voltage across this resistance is determined by the load resistance or the external circuitry, okay? But the current flowing through this resistance or this load is set, okay? No matter what I connect on the external circuit, okay? No matter what I connect across its terminals, across the terminals of the device, the current flowing out is constant, okay? That's the idea. The voltage across these terminals, the voltage across the source is determined by the external load. Okay, that's not constant, that varies. Okay, but for a really large variation in voltage, the current is really constant. Okay, that's the idea of a current source. It provides constant current. Okay, let me go back and do the same thing for voltage source. Provides constant voltage across its terminals. Okay. All right. So these are independent sources. Independent sources. Okay. They're independent of any other circuit variable. But there can be another kind of source, voltage source, okay, called dependent sources. Okay, let me add a page here. Let's see. Add a page over there. Dependent sources. Okay, for dependent sources, the expression, the underlying logic is that the output variable is some gain times input. Okay, so I'll give you an example. Let's say the input is current, the output is voltage. Okay, some gain times current. Okay, then if I have a source, so in other words, what you want to understand is that the independent sources, okay, there can be 4 kinds. Okay, let me duplicate this. Okay, let's see if the input is a current and the output is a voltage. Okay, so let me write it out on this corner here. Input is current, output is voltage. Then I have a current controlled voltage source. Okay, a voltage source. Let me do another thing here. So this is the underlying phenomenon, right? The underlying equation is that the output is dependent on some input. Okay, similarly, the output here, the output voltage, this guy, is dependent on the current. Okay, the output voltage is dependent on the current. We'll see examples for that. There can be another type. There can be a current output, okay, where the input is current and the output is current as well. Okay, and we look at problems involving this. That will make it much more clear. But for now, just let's try to list the kinds of dependent sources possible. Okay, then we have a current controlled current source. Okay, because this is fundamentally a current source. Okay, I output, the output is a current, the input is a current, then I have a current controlled current source. Similarly, when the input is a voltage and the output is a voltage, guess what we have here? We have a voltage controlled voltage source. Okay, voltage control voltage source. Similarly, on the other hand, if I have the input to be voltage and the output to be current, and I'm showing the output using the arrow here for a current, using plus and minus sign for a voltage. Okay, if the output is a voltage, I'm showing that as a plus and minus sign. If it's a output is a current, I'm showing it as an arrow. Okay, so this is a voltage controlled current source. Okay, voltage control is the input, current source is the output. The current source is the output. Okay, does that make sense? So similarly, the exact same thing here. The output is current. Okay, because it is current, I have current source. Similarly, the input is a voltage down here, bottom right. Input is a voltage. Therefore, I'm showing the current control mechanism. Okay. So based on this understanding, let's look at the dependent sources. Don't worry too much. Don't pay too much attention to the terminology here. It's a very simple idea. The input is a voltage. Okay. So that's let's see. The input is Vx is a voltage. That's voltage control. The output is a current. The output is a voltage. I'm sorry. That's the output. That's the voltage source. Similarly, as I mentioned, let me output is some gain times input. Okay, so the output I'm showing using the blue highlight, and the input I'm showing using the red highlight or the pink highlight. Okay, in this case, the input on the right, voltage controlled current source, is Vx. It's a voltage, therefore it's a voltage controlled device. And what's the output? Output, as I mentioned, I'm going to show using the blue highlight. Is IS. It's a current source. So you see that there's an arrow corresponding to that. Similarly, okay, the input is a current, so it's a current controlled device, and the output is also a current, therefore it's a current source. Okay, so the same thing applies here as well. The output is a voltage, therefore voltage source, and then the input is a current, therefore it's a current controlled device. Does that make sense? Okay, we'll come back to applying these principles in problems shortly. Okay, let's see if there are any questions so far. Questions, please, something in the chat window. Can voltage vary or is it always constant? Diana, were you talking about the independent sources or the dependent sources?
The independent source. I think it would. asked that question on the first slide we went over, and then I think in the second slide the voltage did vary with the current.
For the current source, let me go back. This guy, right?
Yes.
Yes. If it's a voltage source shown as plus and minus, voltage does not vary, provides a constant current. So you're right. On the first slide, voltage is constant. On the second slide, voltage varies, but the current is constant because it's a current source. So on the second slide for a current source, voltage is varying, but the current is constant. Does that make sense?
Yes, that makes sense.
Perfect. Thank you. All right. So that's the idea of sources, dependent sources and independent sources. Let's see. Let's go back to Cameron. Did you promise you're going to keep an eye on the chat window? Was it Cameron or was it somebody else? Let's see. Let's look at Diana. Would you be able to do that?
I can do that.
Keep an eye on the chat. I appreciate it. Keep an eye on the chat window. If somebody types a question or something, just alert me. I'll go back to that question. I appreciate it. All right. So let's quickly look at Ohm's law. Okay, the fundamental law that applies in electrical engineering that relates what is known as galvanic circuits. Okay, resistance. Okay, resistance is the capacity of materials to impede, to impede the flow of electrical charge. Okay, there is this device called resistance that by nature prevents or impedes the flow of electrical charge, and it simply heats up. Okay, so resistor gets hot. Okay, resistor gets it dissipates a lot of heat. Okay, resistance is one of the three main components that we'll be looking at. Okay, the other two being capacitance and inductance. Capacitance in farads and inductance in Henry. Resistance is in ohms. Okay, resistance is in units of ohms. Okay, it's one of the three main concepts that we look at in this class. Okay, resistance is the ability of materials to impede the flow of electric charge. Okay, I'll give you an analogy. Okay, think of a road. Okay, and then the stop signs. Okay, the signal lights and the speed bumps. Okay, okay. Think of these as the components of resistance in a traffic flow. Okay, so I'm going to relate the idea of traffic flow to current, and then resistance in that context is going to be similar to your stop sign, signals, red signals, and speed bumps. The combined effect of all of these contributes to the resistance along a road. Okay, and then we'll stretch this analogy a little further when we talk about series resistances and parallel resistances. Okay, and try to gain an intuitive understanding. Okay, resistors, similar current flow, so on and so forth. Okay, resistor is a passive element and it stores no energy. And then in our very simplified linear lump parameter model, the relationship between the voltage across the resistor and the current through the resistor is given by V is IR. Okay, V is IR, where I is constant. So if you were to plot current as a function of voltage, and this is called Ohm's law. Okay, the idea that as you increase the amount of current flowing through a resistance, the voltage dropped across increases, and it increases at a constant slope, where the slope is called as resistance. Okay, so that's the idea. The slope of this curve is called resistance. Now the idea is this formula V is IR is fundamental to our electrical circuits, and we use this over and over again. Whenever I say Ohm's law, it should conjure up this V equals to IR formula. Okay, the voltage across a resistance is directly proportional to the current through the resistance. Okay, George Simon Ohm discovered this. He was apparently a brilliant scientist. Okay, and then the manifestation of this Ohm's law can be in three different forms. I is V over R, or R in more than these forms, actually, as a matter of fact. But the idea is that I times R gives you the voltage across the resistance. Okay, that's the idea of Ohm's law. Okay, and a parallel and a reciprocal of resistance is called as conductance. Okay, conductance represented using the symbol G is the reciprocal of resistance. Okay, conductance is the reciprocal of resistance, 1 over R. Okay, and then all the formulae that we looked at earlier, V is I over V is I over I times R has a parallel as V is I over G. Okay, so on and so forth. We can use them interchangeably. G can be used as 1 over R, or R can be used as 1 over G. Okay, G is conductance, R is the resistance. Okay, so that's the idea. Now, a certain few assumptions are that we are using ideal resistor. The value of the resistor does not vary with the parameters as temperature, the current flow, voltage across the aging of material. We assume an ideal resistance for our purposes, which is not always the case. There is no such thing as an ideal resistance. Okay, but we will assume ideal behavior anyways for this course. Okay, typically resistances shown with some color banding, okay, have some kind of tolerance, okay, plus or minus 10%, plus or minus 5%, so on and so forth. They have a significant amount of variation around the nominal value. Okay, but then we assume constant resistance. Here, so let's revisit the idea of power. Power, earlier we defined it to be voltage times current, okay, V times I. If it was positive, we called it absorbing. If it was negative, we called it delivering power. Now what we can do is we can rearrange using Ohm's law. You know, V equals to IR implies I equals to V over R. So that's what I plug in here for I, V over R. Getting power is V squared by R. Okay, so this is one of the familiar or one of the popular forms of power, calculating power through a resistance. Okay, calculating power through a resistance. I can also do power is I squared times R. Okay, if I were to do this, if I were to replace V as I times R using Ohm's law, then I can see that power is I squared times R. Okay, I can do power is I squared times R. So we use these two expressions for power frequently, comfortably, and interchangeably, wherever we need to calculate the power to resistance. Okay, the resistance only gets hot, and any other result in a resistance power calculation means there's a definition error. If you see a negative power for some reason, there's some error in definition. We'll come back to revisiting that. Okay, so Kirchhoff's laws. Okay, let's do Kirchhoff's laws. Okay, so the idea is that when you're looking at a circuit that has nodes, so this is an addition to the topics or the list of tools. Okay, the first one was passive sign convention. The second tool in your tool set is Kirchhoff's current law. Okay, the next set is Kirchhoff's voltage law. Okay, we're going to look at we're going to add two more tools to your arsenal of circuit analysis tools. Okay, so we looked at passive sign convention, Kirchhoff's current law, and Kirchhoff's voltage law is what we will do today. Okay, so the idea of solving for a circuit, when you want to solve for a circuit, we employ one, two, or more of these techniques. Okay, we use them often seamlessly to be able to solve a circuit. What do I mean by solving a circuit? By solving a circuit, what I mean is this is the part of analysis, means finding all node voltages. Okay, also finding all branch currents. This is what I mean by solving a circuit. Okay, when I say solve the circuit, I simply am asking find all the node voltages, find all the branch currents, or at least those of interest to us. Okay, that's what I mean. Okay, so let's look at Kirchhoff's current law. It simply says, okay, the sum of currents at any node is zero. Okay, so it is based on the fact, so conservation of charge. Okay, that's the underlying principle for this Kirchhoff's current law, which says the sum of currents at a branch is zero. And I'll show you an example here. Okay, let's say I have at a node, let's say I have a node that looks like so. Okay, a node is a connection of more than one branches. Okay, let's say I have 4 branches. Okay, 4 branches emanating from this node. Okay, this dot is called a node. Okay, this guy is called a node. Okay, and these are called, the rest are called the branches. Okay, so now the idea is the amount of current flowing in, okay, to any branch, the sum of those currents. Let's say there is this branch I1, the current I2 flowing into that branch, I3, I4, I5, and I6. Okay, Kirchhoff's current law says if you sum all the currents If you sum all the currents in these branches, let me see if I can use a different color there. Okay, so I'll use that color. Okay, if you can sum all the currents in these branches, that equates to 0. Okay, so there is no current at a given node, at that particular node, or any node. Okay, if you sum all the currents in a node, at a node, that is 0. Okay, so let's see the application of this guy. Okay, this is where it really gets interesting. Okay, so if you look at a circuit that appears complicated, how many nodes are there? Let's count the number of nodes. Okay, there's one node A over there. Node is something, a connection of more than one branches. Okay, well, sure enough, you see 1, 2, 3, 4 paths coming out of this one point. So I can call that a node. Okay, similarly, there are 3 paths coming out of this point. So I'm going to call this guy a node as well. Okay, however, let's pay particular attention to the one in the middle. That guy is not a node because there is no connection over there. There is no connection between the vertical line and horizontal line. They're separate. Okay, all right, so let's see if we can apply the Ohm's law, the Kirchhoff's current law here, Kirchhoff's current law, okay, at node D. Okay, so there's more than one ways to do it, and I'm going to give you 2 ways. Okay, and I don't want you to confuse between these 2 techniques. Okay, they're the same. They're essentially the same. Okay, the first one is to use this convention. When you're looking at a current that is coming in, call it negative. When you're using a current, when you see a current that is going out, call it positive. So I'm showing you techniques to apply Kirchhoff's current law, okay, and some standards that you want to follow. Let's apply KCL at node D first, okay? So in order to do that, any current that is coming into the node is considered as negative, and any current that is leaving the node, and there are 3 currents that are leaving the node here, okay? If you think about it, there is one current I5 that is leaving, okay? You see the arrow pointing outwards from D. Similarly, there is a current IA leaving upwards, okay, out of D. Similarly, there is another current IC, okay, IC current leaving that. Okay, so according to Kirchhoff's law, when you add all the currents, I5 with a positive sign because that is leaving. Similarly, IA with a positive sign because that is leaving too, plus IC with a positive sign because that guy is leaving as well. That should sum to 0. Okay, does that make sense?
Yes.
Now let's see if that is what we have here at node D. IA plus IC plus I5 is 0. So let's see if we can do the exact same thing at another node. Okay, let's see at node. So KCL at node C. That's this guy. Okay, that's this node here. Let's see if we can look at the currents. Okay, this node. Now, if you think about it, there is one current I3. Okay, there is one current I3 coming in. So because it is coming in, I'm going to call it negative. negative I3, and there is another current IC coming in. Okay, so I'm going to, because it is coming in, I'm going to call it as negative IC. And then pay attention to this guy, I4, coming through this branch. You see? So I4 current is coming from the left in. So coming in, I'm going to call it as negative. Did I forget any other current?
What about IB?
IB, thank you. What about IB? IB is leaving that node, right? IB is leaving that node. So I'm going to call it a positive. Does that make sense? So KCL at node C, you look at all the currents. Essentially, I'm adding all the currents. The currents that are coming in, I incorporate a negative sign. The currents that are flowing out, I incorporate a positive sign. Okay, do we want to do this at node A as well? Shall we do that at node A as well? Okay.
Yes.
Let's do KCL at, do you want to help me?
Sure. So at node A, I see I5 is going into node A. And so that,
Therefore, I put a negative I5.
yes. And then
Okay.
I2 will also be negative. And then I4 and I1 will be positive, and this will be equal to 0.
Plus I1 equals to 0, right? So that's KCL at node A. Okay, so I can do that at a bunch of different nodes. KCL at node C, okay? KCL at node D. Okay, so that's the idea of KCL. Oftentimes, and I'm going to show you something different here. It's not really different, okay? This is one mechanism to use it, okay? One technique to use it. And you can stick to this and you will always arrive at the right answer, okay? The other technique, the one that I prefer, I'm going to show that at node B, okay? At node B. At node B, what are the currents coming in? There is current coming in as I1, okay? There is current coming in as IB, and then there is current coming in through IA, is it? Let's call it IA, okay? And what are the currents leaving? The currents leaving are I2, okay, and I3, okay? So I have 5 currents coming in. So the technique I use, and both of these are exactly the same. I don't want you to confuse between the two. They're exactly the same. KCL at node B, okay? What I do is I forget about the signs. I do not worry about the positive or negative sign. I add all the currents coming in on one side. So I1 plus IA plus IB. And then I add all the currents leaving on the other side, I2 plus I3. Okay, that's exactly the same as doing this. Okay, that's exactly the same as saying, I'm going to consider this as a negative sign. I'm going to consider, I'm going to consider this guy as a negative, IA as a negative, IB as a negative, and add to I, equate that to 0. So instead of paying attention to sign, what I have done is I added all the currents coming in on one side with a positive sign, okay? And I added all the currents going out on the other side, currents coming in, going out. okay, and I equate them. That's, you could use either of these techniques, absolutely fine. They're exactly the same. As a matter of fact, as I showed you, if you bring them to the other side, it is consistent, okay? So it really is not a big deal at all, okay? Use whichever one works for you. Okay, one convention is to use negative sign for currents coming in and positive sign for currents going out. Or my technique of using them is add all the currents coming in to one side and currents going out to the other side, equate them. They're exactly the same. So that's the idea of Kirchhoff's current law, which is a manifestation of um, conservation of charge. Okay, conservation of charge. Okay, let's see. Let's look at another idea here, Kirchhoff's voltage law. Okay, so far we looked at currents at a node. Now we are going to look at voltage around a loop. Okay, and this is better. The idea is that the sum of voltages around any closed path equals 0. Okay, and I'm not going to elaborate on that theory there. It is better explained using an example. Okay, this is the idea of conservation of energy. So let's see if I have a circuit that looks like this. Okay, there are a bunch of different closed paths here. First of all, let me try to identify the closed paths here. Okay, there is one path that looks like this. Okay, let's see if I can build that. Okay, so there's one path that looks like this. Okay, let's see if there are more closed paths. Sure enough, there are a ton of closed paths here. So look at this guy. That's a closed path. Okay, so in other words, any closed path is a path that begins at a node. For example, let's say I want to begin at this node. Okay, goes around and comes back and ends at the same node. Okay, I'll give you an example here. Let's see, let's pick a different color, this guy. So beginning at that node, okay, right there, I'm going to traverse a path and end at the same node. That's a closed path. Okay. Similarly, I can think of any number of closed paths here. There's more than one closed path. This guy. That's a closed path too. Okay. So typically what we do is there may often be more closed paths than I need oftentimes. So this guy is a closed path. Okay. So there are a bunch of different paths. So this is called a loop. Okay. A closed path is called a loop. Okay, so Kirchhoff's voltage law is applied around a loop. Okay, and let me show you. We add the voltages around the loop, add the voltage drop around the loop, and equate them to 0. Okay, we'll pick one loop for example. Okay, one loop that begins here and ends like so. Let's call this loop A. Okay, let's call this loop A. Okay, the way you apply Kirchhoff's voltage law is to begin at the lower left corner of the loop, lower left corner of the loop, and go around the loop once. Okay, go around the loop once and add the voltage drops. Okay, this is what I'm going to do. So pay attention. I'm going to follow this path here, begin over there, traverse through all the elements in the loop. Okay, so first in my traverse, I find this resistance, okay, showing a voltage drop negative to positive V1. So I add a negative V1 over there. Then I see the resistance 2 ohm resistance with a plus or minus V2 over there. And it clearly shows a positive sign on V2. So I add a plus V2 over there. So that's the here. Then I come to the 4 ohm resistance with plus minus signs shown like so. So plus 4, sorry, V4. Okay. So I'm going element by element. Okay. One by one. I'm traversing all the circuit elements one by one in this path. Okay. What's the next element? The next element is a voltage source over there with the negative and positive sign. So the negative comes first. So I'm going to do a negative VB. Okay. And then there is this guy. Then there is a negative VB. Excuse me. Then there is this guy, negative positive V3. Okay. So negative V3, all of that equals to 0. So around the loop A, negative V1 plus V2 plus V4 minus VB minus V3 equals to 0. That's the idea of Kirchhoff's voltage law. You add the voltage drops around a loop, that should sum to 0. Okay. Earlier, Kirchhoff's current law, you add currents at a node. Okay. When you add currents at a particular node, that summed to 0. Here, when you add voltages around a loop, that should sum to 0. We'll do another example here. Let's see. Let's pick another loop. Loop maybe that's like so. Okay, let's pick that loop. So I think this loop is already called as loop D. Let's not loop, let's call this loop E. Okay, that's not shown here. Let's do loop E. Begin at the lower left corner, okay, and follow the circuit elements. Then the first circuit element that you see is the 6 ohm resistance in here, okay. The 6 ohm resistance, notice the polarity plus minus V6. So that comes first, plus V6. Then I follow the path to find a 7 ohm resistance. Plus comes first, plus V7. Okay. And then I look at the VD. Negative comes first, negative VD equals to 0. So this is KVL around loop E. Okay. That's something that we just defined to be a loop. Does that make sense?
Yes.
Okay. So we look at some example problems. That way it becomes absolutely clear. Okay. So that's the idea of KCL and KVL. So far we looked at 3 techniques. Okay. The first technique was passive sign convention. The second technique is Kirchhoff's current law. The third one is Kirchhoff's voltage law. Okay. All right. So let's look at example problem here. The example problem asks us to do KCL application. Apply KVL. Okay, so the idea is to solve. Okay, solve the following circuits, or sometimes they may ask you to find the power dissipated in the 20 ohm resistance. Then it simply means find the voltage across this resistance V, and find the current across this resistance, and multiply the voltage and the current to get VI. Okay, so that could be one way of asking the exact same thing, solving for the circuit. Okay, so the first thing we are going to do is to, so let's see, let's call this I1, let's call this I0, and I'm going to define some currents. I'm going to call this current, and I'm going to make these definitions. I2, okay, the current through the 13 ohm resistance, I'm going to call that as I2, okay, and this current, I'm defining it to be I3. Okay, so pay attention to the fact that these are the definition and directions that I am giving. I'm choosing these voltage and current directions, and as long as I'm consistent with these directions and this polarity throughout the problem, it will lead me to the right answer. Okay, so the next branch current that I'm going to look at is this guy, the current through the 8 ohm resistance. I'm going to call this as I4. Okay, I'm going to call this as I4. So my idea, the idea is I want to be able to find out the total current that is supplied by the power supply, the voltage source. Let me call this as I source. Okay, so I want to be able to tell the value of I1. I want to know the value of I2. I want to know the value of I3 and I4. Okay, what are the values here? Okay, what are the different values of I1 to I3? That's the idea of solving this circuit. Okay, so the first thing we are going to do is this guy. Identify some nodes. Let me call this as node. Okay, let me call that as node A. I'll call this as node A. Okay, I'll call this guy as node B. That will be my node B. Okay, I'll call this guy as node C. Okay, and then this guy as node D. Okay, later on we'll come back to define node D to be ground at a later time. But for now, we leave it like that. Okay, there are 4 nodes. Okay, and then we'll come back and do some more. Okay, let me see if I can. Okay, node A, B, C, and D. The first thing I'm going to do is to solve this circuit. The first thing I'm going to do, solution, is to set up equations. Okay, the first thing to do is to apply KCL, Kirchhoffs Current Law, at node A. Let me apply KCL at node A. Okay, KCL says, like I mentioned, look at all the currents coming in on one side. Okay, the current coming in is IS. Okay, from top to bottom, and equate that to the currents leaving, I2 plus I4. Everybody with me?
Yes.
Okay, so that's the step 1. The next step I'm going to do is to apply KCL at another node. Okay, so apply KCL at node B. Okay, this is all in an effort to find all the unknowns. I have 4 unknowns or 5 unknowns. I need a bunch of 5 equations. Let me not forget this guy, I naught. Okay, there's an I naught as well. So there's more than 4, 5 unknowns, I naught. I should be able to calculate a value for that as well. Okay, so KCL at node B, when I apply KCL at node B, that's this node, I have to look at the current coming in. What's the current coming in here?
At node B, the current coming in is I2.
Current coming in is I2. And what's the current leaving?
That would be I3 and I1.
Thank you. Okay, so I have KCL at node B. Let me apply KCL at node C as well. So I apply KCL at node C. There is 2 currents coming in. There is I3 coming in from left and I4 coming in from the left on the top, 8 ohm resistance. So I3 plus I4 equals to I2. I naught is the current going up, going down, right? I naught is I3 plus I4. Okay, so let's do KCL at node D as well. KCL at node D, the currents coming in are I1 and I0, and the current leaving is IS. Okay, so the current leaving is IS, that is equals to I1 plus I0. Everybody with me?
Yes.
Okay. So now what we can do is in the problem, I think, and I have forgotten to mention that I naught has been given to be 2 amperes. I naught has been, sorry about that. I naught has been given to be 2 amperes. I naught is given to be 2 amperes, and we should be able to do the calculations. We have 5 unknowns, okay, including IS. Okay, I1, I2, I3, I4, and IS. Okay, we have these 5 unknowns. We need 5 equations. Okay, so we better set up one more equation. Sometimes it may be that these equations are dependent, and these equations we end up needing one more extra equation. Okay, so in order to do that, this is what I'm going to do. I'm going to apply KVL around loop alpha. Okay, so I'm going to define a new loop here. So before I do that, let me color code them carefully. Okay, I'm going to change them to this color, okay, nodes, just so it doesn't overlap. Now I'm going to come back and define a loop here. See? Let's call this loop alpha. Okay, let's call this loop alpha. Let's call this loop alpha and try to You know what? I think I better copy this and write it out in a separate page. Okay, that way it's cleaner. Okay. All right. So I'm going to apply, this is called loop alpha. I'm going to apply KVL around loop alpha. So the idea is to begin at the lower left corner. Okay, begin at the lower left corner, follow the path, and add all the voltages that you come across. That's the idea. Right? So let's follow the outer path. We begin at the 80 volts power supply, and then when we begin our journey, we see a negative sign over there. So negative 80 volts. Okay, and then we continue our journey, and then we see a positive sign over there. So 8 ohms times I4. Remember Ohm's law. The voltage dropped across this resistance. Because I'm using KVL around loop alpha, I want to add the voltage drop around the loop. And the voltage dropped around the loop is V times I. Around this 8 ohm resistance is 8 times I. Then I do this. Then I look at plus minus 6 sign, 20 ohms times I naught, the value of which is given to be 2 amperes. Okay, all of that equals to 0. Okay, I naught is 2 amperes. So I can write it as an equation. So from here, I naught is 2 amperes. I can get a value of, so when I plug in a value of 2 amperes here, 2 amperes here, the only unknown is I4. So I4 is going to come out to be, let's say 5 amperes. Okay, I4 is coming out to be 5 amperes from the KVL loop. Okay, we'll use another loop. Okay, we'll do another loop, which is this guy. Okay, that loop over there. Dang it. Okay, that loop. Okay, let me call this loop beta. Let's apply KVL around loop beta. Okay, when I apply KVL around loop beta, I begin at the lower left corner. Okay, begin there, lower left corner, and follow the path. Okay, follow the path. Remember, this was positive and this was negative earlier. So when I follow the path, I see a negative sign first. Okay, so negative 4 ohms times I1 is the voltage dropped across that resistance, 4 ohms resistance, followed by I3 times 4 ohms, positive sign, plus I naught times 20 ohms is 0. Okay, so I'm following the path here to the starting point. Does that make sense? I
Yes.
naught is given to be 20 amperes. Okay. So from this, we should be able to rearrange these equations. And then if you solve the currents here, okay, if you solve the different currents here, if you solve these different equations, so let's see, let me do this. Okay, so I4 was found to be 5 amperes. And if you solve these equations, 1, 2, 3, 4, and 5. Okay, if you solve all of these 5 equations together, it's very straightforward to get the value for I1, I2, I3. So when you solve that, you should see a value for I1 equals to 7 amperes, and I3 is negative 3 amperes. I4 is 5 amperes. Okay, so on and so forth. I2 is 4 amperes, and IS is 9 amperes. Okay, so one quick way to check this is 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 the current coming in 9 amperes should equal I2 plus I4. I2 plus I4 is 9 amperes. That's the current coming in. So current leaving. Okay, so these are the values that you should get. When you solve this simultaneous system of equations. Okay, so when you solve the system of simultaneous equations, 5 equations, you get a value for I1 through IS. Now, questions about this, please. What questions do you have, please? Okay, so this is when we are trying to solve this problem, when we are trying to solve this circuit with the given 2 amperes, all we have to do is set up KCL and KVL equations and then solve the system of linear equations. Okay, let's see, we have about 10 minutes. Let's see if we can solve another problem. Okay, let's see if we can solve this problem. Some parts of the problem are given, and I think just give me 1 second. This is given to be 90 volts. Okay, so how would we go about solving this problem? Example problem. Okay, so questions so far, please. What questions do you have so far about applying KCL and KVL in the circuit? Okay, so let's solve another problem here. Let's do another problem solving the circuit. And this is given to be 90 volts. The 22.5 ohm resistance drops a voltage of 90 ohms. Okay, so what I'm going to do is this. The first thing I'm going to do is to identify some nodes. I'm going to call this as node A, call this as node B, node C, node D. So let me name them node A, node B, node C, node D. Okay, when we want to solve this circuit, okay, it's given to be 20. Okay, now what I'm going to do is to define some currents. Okay, let me define some currents here. Okay, I'm going to call this guy. Okay, if you pay attention, I'm going to call this guy as I1. I'm going to call that guy as I1. Okay, and I'm going to call this current positive on this terminal, positive on, okay, positive on this terminal and negative on this terminal. I'm going to call this current as I2. Okay, that's the way I define it. And as long as I'm consistent throughout the problem with that definition, I'm going to be all right. Then I'll define another current and this is my choice here. I'm going to define this current plus minus the current flowing through the 20 ohm resistance to be I3. Okay, does that make sense? Now I'm going to define this direction plus minus the current flowing in this resistance to be I4. Okay, similarly, I'm going to call this resistance current in this resistance. Okay, the 4 ohms resistance, I'm going to call this to be I5. Okay, and then the current in this branch, in this voltage source, I'm going to call this to be I total. Okay, questions please, questions so far. These are the current directions that I chose.
Is this circuit a Wheatstone bridge?
It's similar to, okay. You see that two diagonals are connected in between by a resistance. So it can be implemented, it can be transformed to a Wheatstone bridge, sure, yes. What other questions, please? That's a good question. That's a good point. So everybody okay with me writing this, defining the currents this way?
Yes.
Okay, so let's go to this solution then. Okay, I'm going to probably quickly write solution here and then let you solve that. The first thing I'm going to do is to set up KCL at node A. Okay, first of all, do we know the value for I1? Is there any way for us to know the value for I1? Well, there is, because remember the voltage across the 22.5 ohm resistance has been given to be 90 ohms. So the I can be obtained by V over R, Ohm's law. Okay, so it's going to be 4 amperes. I'm interested in finding the rest of the currents, I2 through I5 and I total. So in order to do that, let me set up the KCL at node A. Okay, the current coming in is I total. That should equal the current leaving I1 plus I5. Okay, so that's equation number 1. So I can also set up KCL at node B. Okay, let me write KCL at node B. The current coming in is this guy. I didn't want to do that. The current coming in is this guy and this guy. That should equal I2. Okay, so the idea is, I2, the current leaving, should equal the current coming in I1 plus I4. Okay, I1 plus I4. I1 is again 4 amperes. Remember, I1 plus I4. Did I forget anything else? Okay, I2 is I1 plus I4. Let's write KCL at node C. At node C, that's this guy at the bottom. What are the currents coming in?
That would be I2 and I3.
Okay, what's the current leaving?
IT.
IT, thank you. I total equals to I2 plus I3. So this is equation number 2. Here is equation number 3. Okay, so let's do KCL at node B. KCL at node B. Okay, when I look at KCL at node D, which is, okay, this guy, okay, this guy, the current coming in is I5. That should equal to the current leaving I4 plus I3. Okay, so I5 equals I3 plus I4. This is my current equation number 4. Okay, so I need one more equation to solve for the unknowns. Okay, I need one more equation to solve for the unknowns. There is a total of 5 unknowns: I2, I3, I4, I5, and I total 5 unknowns. So I would need one more equation, or maybe sometimes if the equations are redundant or trivial, we need more than 5 equations. So what I'm going to do is I'm going to look at a loop, KVL loop. Okay, and I'm going to be very, very smart in selecting my loop. I'm going to select this guy as a loop. Okay, I'm going to select that guy as a loop and make the field 0. Okay, let me call that loop alpha. Okay, color coded using purple, loop alpha. Okay, KVL around loop alpha. The question you want to think about is, what made me choose that loop of all the loops available? Okay, but here I'm going to write the equation here, follow the process, which is to begin at the lower left corner, okay, and then follow the path. Okay, so first I see a negative 240 volts, okay, and then come around, see this plus 90 volts, okay, and then follow the 15 ohm resistance, 15 ohms into I2 equals to 0, which should give me a value for I2 should be, okay, I2 should be 10 amperes. Okay, I2 should be 10 amperes. From that, I should be able to calculate more. Okay, once I have I2, okay, I have I2 and I have I1, I should be able to calculate I4, right? Because I2 is known to be 10 amperes. I1 is given not directly but indirectly to be 4 amperes. So I4 should be 6 amperes. Okay, so let's see if I can apply one more KVL. Okay, I'm going to apply KVL one more time using this loop over here. Okay, when I apply KVL around that loop, okay, begin at the lower left, which is this guy. Begin at the lower left corner and then follow along the loop. The equation that I'm going to get, KVL around loop beta. Okay, let me call the green one as loop beta, is negative 4 into I5 plus 90 volts, negative 5 into I4. Okay, so this is going to be the equation. The equation I get will be, and I welcome you to go back and double check that, 4 ohms into negative I5 plus 90 volts, negative 5 into I4 equals to 0. So you have a bunch of equations now. So 1, 2, 3, 4, 5, 6 equations, 5 and 6 equations. From this, you should be able to solve for all the unknowns. Okay, but I want to leave that as an exercise for you. Does that make sense? So questions about this, please. Okay, when we come back tomorrow, I'm going to talk about this a little bit more and tell you why I chose these particular loops. Or maybe it may be a good idea for you to look into the problem and see why I chose the loops that I chose here. Okay, so we'll stop here unless there are questions. Okay, I'll see you folks